This computer. Okay. So, as I told, we continue our practical tasks. Last week, we discussed how to design an overcurrent protection. So I want to highlight that you have a homework for this subject. It means that if you want to have a grade, yes, you need to do your homework. So all video records will be available. Yes, last week we had a stream on YouTube as always. Yeah, like it is. But for today, I'll use a record via Zoom and I'll place this record to YouTube. Okay, so today we will continue. So typically, this is the third task. So last week we discussed how to do first two tasks, and now we'll discuss how to do the third task. The file with task description will be available in Ortus as well. Okay, so our task. What is your task? I open the scheme. So you need to draw current and voltage vectors for a protection device in case of fault somewhere. So this is overall task. Now let's talk in details. So we have a scheme. Whatever, it could be transmission level or distribution level, typically. Of course, if we are talking for distance protection, yes, it means that it is transmission level because we don't use such expensive protections in distribution level. Typically, distance protection is for transmission level. But in our case, we are not making a protection design. We just want to know how the fault looks for the protection device. So in this case, we could discuss, for example, like it is an example for, let's talk about the protection A. So here we have 3 lines, and we're talking about the line protection. So if we call it line protection, it means that the main task is protect the line. For example, if we talk about the protection A, it means that its main task to protect the line number 1. The same is for line number 2 and for line number 3. So here we have a loop, and it means that this is quite complicated task for protections, yes, to not to detect fault, but to make a selective operation. What does it mean? So the question is, what protection device must operate first, what must operate second, and so on. So we need to understand what will be the sequence of operation. Because if we have a radial network, so all linear lines are in series, it is very clear that the nearest to the fault location protection device should operate first. Why? Because we need to isolate this fault from the network. In this case, for example, if we have a fault on a bus number 2, there is a big question: what protection device should operate, and as well what circuit breakers should operate. So here is very simple because it's an example. So protection device A operate protection circuit breaker A as well. So here you see, if we have the fault on bus number 2, from your point of view, what protection device should operate? Sorry?
G2.
Number D and? You said D and?
G2. I said B.
Okay, your
B
colleagues say B.
B and E.
B and E. But sorry, you said B2. D2?
G2.
Well, okay, D2. Sorry, I can't understand what does it mean. D, it's a letter, yes? It's a name of protection device. But what is 2? D2. What is 2? It's a number? It's a digit?
Digit.
Digit 2. What's the meaning of the letter of the digit 2?
Say generator 2.
D2, D as well?
G2. You said G2. Generator 2.
J.
You say J. Okay.
J. Okay, from my D. It's a letter A B C D, not J. That's why J2. Okay, it's clear for me. No, okay. This is I understood your expectations, but sorry guys, you are wrong, of course, because first of all, this is very complicated question. But in this case, let's discuss the first suggestion about B and E. Just an example. Okay, so you understand that, okay, we could separate the network from the bus number 2, but in this case, B and E could be the good choice. Could be the good choice because they are, how to say, the nearest to the fault in this logic, yes. But if the fault will move to the bus number 3, for example, yes, or to the bus number 2, it means that other protection device like F, D, A, and C must operate. But how we could explain to the protection device that sequence is different? Okay, we will not waste our time to explain this complicated task because it was described during your lectures. For our task, we need to understand the logic, only the logic. So, all to make a design for this sequence, for this series operation, we need to use directed protections because fault could appear in any place, and in this case the sequence of operation is different. And how we make this sequence using time delay, because we have two criteria how we could understand what to do. First of all, we need to detect the fault. We could detect the fault using different values, for example, because we have three main values: current, voltage, and impedance. For this case, if we call talking about this distance protection, we are talking about the impedance. If we're talking about the simplest, the current protection, we are talking about the current value, so fault current value. In this case, if we have fault current, so protection device must detect this fault using current values, and the second, time delay, makes the selective operation. The logic is very simple. The nearest to the fault protection device has the lowest time delay, and the far we are from the fault, the more the higher, the greater current time delay value we have. So it means that if we could have the radial network when we have only one source and all the network in series, the nearest to the load protection device has the lowest time delay, and the nearest to the power source relay protection has the greater time delay. Why do we need this? Because we need to design protections like all relay could detect the fault. So, but operation sequence we make using time delay. The lowest time delay, it means that it operates first, and so on in this logic. But as I said, all this information is in your lectures. Now we have practical task. And first, what do we need? We need to understand how protection device could detect or could see how the fault. Because, for example, we have all books with vectors. How mathematically fault looks like, yes? But our protection, for example, no, we continue with the example when we have a fault location on bus number 2. But how protection device A could see this fault? Because as we know, this is bus number 2. This is the impedance of line number 1. Of course, we have more impedance, because this is complicated, but just to understand, this is that impedance. Voltage values here are not the same as voltage here, of course. And if it is a distance protection that calculates the impedance, of course, the main idea is the Ohm law. Yep. We need to calculate the impedance from the place where protection is located to the fault location. And this impedance will say to our protection device, is it fault or not? Now, this is the logic about this distance protection operation. But as we understand, to calculate the impedance, we need to know voltage and current. And this is complicated because well, it's complicated for detection, because for calculation, not for physics. Voltage are different in bus 1 and bus 2. Okay, current. Okay. Device A, device B. Okay, we will see the same current, but voltage is different. And this is very interesting, how voltage and current values, vector values, will look like here. And this is our task. First task. Of course, this will be our first and the last task, but it's enough for you because this is quite complicated. Just to operate with equivalent schemes for such complicated tasks and calculate such complicated scheme, it is enough for our subject. Okay, first of all, we try to learn how to make an equivalent scheme for this network and how to calculate currents and voltages for this scheme. We will use basically voltage potential approach or method, whatever. And to do this, you have a MATLAB code that will help you to do this. But you need, to understand the logic and how to use this. Okay, so this is how your home task network looks like. For our discussion, I'll use a little bit another network. Similar, but a little bit different. Okay, I'll use this one. I'll use this one. Okay. I want to make it a little bit compact to be possible to compare two schemes. Okay. I put it here. So, yes.
The recording of this class will be in the Otus, right?
Is the link to YouTube
Okay.
record will be in your Ortus. Yes. Okay. So what? And I'll prepare you a document with task and description.
Oh.
So to be easier, I understand that this is really complicated for you. Sorry, guys, but to be honest, your bachelor level is really low for our master program. This is the issue. Okay, so what we see? We compare two schemes. So we have a loop of three lines. Line number 2, 1, and 3. The same we see here. All lines, of course, because it is loop, have protection device in every end of the line. It is very easy. If we have a radial network, it's enough to have one protection and one socket breaker, because we have supply from this side, and if we disconnect this one, we'll disconnect everything here from the supply, so no problem. Disconnect the fault element from the supply. In this case, when we have loop and we have supply from different points, yes, like it is standard network, because for transmission network, we always try to make loops because it is more safe, because we have possibility to supply from different substations. And in case of trouble in any element, for example, transformer here or something else, bus and so on, we could supply from the another side and every consumer will be happy. That's why, of course, for distribution network, from protection point of view, very often try to keep this radial condition. So to, for example, to switch off one, for example, line, yes, to keep this like a radial, not to have a loop, because for distribution network, the loop is quite complicated. Why? Because it is not clear what, like here, for protection device, not clear where is the nearest protection device to the power supply and nearest to the fault, because it is a loop. It's complicated. But for transmission network, because transmission network keeps this power system, this is very important. And in case when we keep this loop, we need to use possibility to disconnect the fault element from every side, yes, because we have bidirectional power supply. We need circuit breaker here and here. We have protection device here, and as well, we need to use directed protection. So what does it, once more time, what does it mean directed protection? It means that every protection device has its operation direction. So if we have current fault, this one, and the direction of current fault is the same as protection device direction, we could operate. So it is our client, it is our task. If current, faulty current, real flow is opposite the protection device direction, it means that this is not our client. We're ignoring it. Why? Because we need to to ensure this selective operation. So this is very short how this must be. So that's why we have protection devices and circuit breakers from every side, from in every line. Okay, so what is the same? What is the difference? So here we have bus number 3. Bus number 3. Here we have transformer for loads. Here we have one transformer. Is it any difference from our point of view? No. For our protection device, this doesn't matter. Because this is the side for the consumer. We are protecting clients, not protecting this. Whatever. The only one what is different, here we have two systems, and every system has its substation with transformer. Here we have only one system, here, and two generated transformers here. What is the main difference between two schemes? So we'll learn how to calculate using this scheme. Your homework will be to do with this scheme. Once more time, what is this? What is system? The system is what we just concentrate or unite all elements from any parts of power system to one power source. So system is some equivalent. That's why we could call everything what is in this side like a system and connect it here. Yes, so this is a system. Okay. So now we use this scheme and go down, sorry. If we want to calculate currents and voltages for this bidirectional power supply scheme with a loop, the only way is to use this symmetrical component theory. And this theory contains of 3 main sequences. So we need to represent this network with 3 equivalent schemes. Positive sequence equivalent scheme, negative sequence equivalent scheme, and 0 sequence equivalent scheme. And to connect these 3 sequences together to one equivalent scheme. This is an example how this could be. So, one remark, very important. We have different types of fault. We have symmetrical fault, we have asymmetrical fault, yes? If we have 3-phase fault, we have symmetrical fault. And this is the simplest scenario, because we just need positive sequence equivalent scheme. We just represent transformer with impedance, line with impedance, generator with impedance, yes? To construct an equivalent scheme and to calculate, nothing special. But if we have asymmetrical fault, 1-phase fault or 2 phases fault, yes, this is more complicated. And we must use not only the positive sequence scheme, but negative and 0 as well. So if we have a ground fault, so, or in other words, 1-phase fault. Ground fault is when one phase is connected to the ground. Yeah? We use positive sequence scheme. It is here, the upper loop, and inside. Okay, you could see this is a mark with the sequence name. Here, all elements if with number 1. For negative sequence, all elements has number 2, index, yes. And for 0 sequence, all elements has index 0. Very simple. So we need this is one positive sequence, this one is negative, and this one is zero sequence. All three sequences. If we have two-phase fault, so in other words, fault that is not connecting to the ground. We don't use zero sequence, but zero sequence appear when we have a ground. Only two sequences, positive and negative. But the way how they are connected together is a little bit different. So here, maybe I'll draw on the board a very simple but very clear explanation how they are connected. So we represent, for example, very simple generator, protection device. Oh, no, sorry, not protection, but some impedances of network, whatever. Here we have the fault place, yes? So, okay. Network is something like this, for example. Well, this is a network, yes, generator, transformer, line, yes. So, how I represent? This is a fault location. So, this is a positive sequence, PS. If we have two-phase fault, we draw here the negative sequence, connect the point of fault together, and connect this neutral wire to the ground together. This is a logic. If we have one phase fault, like it is an example, or like it is in your homework, we need three sequences. Okay, so I am right, no problem. So this is positive, this is negative. This is a fault location, yes. So we connect positive sequence fault point to the negative sequence neutral wire, negative sequence fault location to the zero sequence neutral wire, and zero sequence fault location connect to the far to the positive sequence neutral wire and ground. This how it is. So based on the fault type, we have different law how we connect sequences together. And this is an example how this should be for ground fault. So here you see we have the line number one before the fault, after the fault. You see the L1. Here is line number two. Maybe I'll put a bit up. And go up. Go up. So here. See, line number one and line number two, they're in series here. And the fault is here. No, okay, the place is here, but it means that theoretically it could be moved somewhere here. And this is the equivalent scheme, and here the fault is somewhere here, because it is universal. Compatible for different places. Okay, so we connect the fault point to the neutral wire of negative sequence, and here is the same to the zero sequence. Okay. So maybe once more time. So what do we need? We need to represent every element of your network to equivalent. So power source to electromotive force, transformer, reactance. Okay, of course, there could be impedance or reactance. We understand that if we talk about the transformer, the main is reactance. So the resistance is very small. That's why we very often replace impedance to reactance, because they're very close. They're similar almost. Impedance is for lines. And in this way, we represent the network. And we draw at once positive, negative, and zero sequence. What is next? The next step is to name all, not to call, to name, whatever, all nodes. Here you see, with a blue, we have numbers for every node. Without one, you see the grounding node, yes? We have numbers for every node except one. So this is the, how to say, the approach that we call only the nodes that are not connected to the ground, because it is a voltage potential method, and the voltage for the ground is zero. That's why we don't need it for calculation, because we will need to divide by zero, and this is impossible. That's why this node does not have a number. We are ignoring it. So, and for every branch, we draw a current direction with red color. And we draw it whatever we want, because the calculator, the result of our calculation, where we will get the values for every current in every branch, will say, is our chosen direction right or it is opposite? So we don't need to care about it. We just briefly choose the direction as we wish. So, okay, this is the second step. So once more, first step, you draw an equivalent scheme. Second step, you, yes, draw current directions for every branch. And here you need to remember, what does it mean, branch? The branch is the connection between two nodes. This is branch. And for example, one branch could contain several, for example, impedances, different real devices. Yes, but as they are in series, we know that the same current is here. Yes, because they are in series. So this is one branch between two nodes, and that's why it is one current. We have current names and node names. Okay, next. Next, we need to fill the matrix. How? Okay, this is in Latvian, but I'll prepare this for in English, especially for you. What do we have here? Here we have nodes. Here we have branches, because node number, so with 9 and branch 7. How we fill this matrix? Very similar. If current flow into the node, we write -1. If current flow out of the node, we write +1. If there is no connection between node and branch, we write 0. Come up. Example. Node number 1. Current number 4 flows out. What do we write in the matrix? +1. Yeah. The same for current number 3. Current number 5. No connection. No connection to the 0. Because we have in matrix, yes, all branches. Because see, all 70. That's why we need to go through all the branches. So, but this is very easy. So we just say what flows out, what flows in, and for all other branches we write zeros. Yeah, so, and this is for every node. Okay, we see, okay, number 2 in, number 5 out, number 3 in. Okay, no other connections. For others, write 0. What is important for such nodes like 4 or 6? Because we see more easy for node number 2, more easier. Number 4 in, number 5 in, but we have number 6 and 17 as well, because this is connection between two sequences. So not forget about this 6 and 7 for special nodes when we have this connection between two sequences. Okay, this is for first matrix, very easy. And we have two more matrices, impedances for branch and electromotive force for branches. More easier. For every branch, we need to write, does it have an electromotive force or no? If it has, and this electromotive force direction is the same as current direction for this branch, write electromotive force value with a plus sign. If not, if opposite, with minus sign. Come back to the scheme. We have electromotive force only for two branches, number 1 and number 2. Only 2 units, yes? And the same in this matrix, first, second branch electromotive forces, all others are 0. And for these branches, just write the impedance or reactance, what we choose, yes, for every branch with 3 matrices. Typically, this is all what you need to do to have a calculation. No, a calculator. That's we could call it, a calculator. Okay, now let's go to see our calculator. This is the Dolgitzer homepage, his own, yes, but I don't know. Where do you have all information about, like only Nortus maybe? Because, for example, here Dolgitzer have for you, no, for foreign students, materials here as well. But I'll discuss with Dolgitzer about all these materials. But because here we go a MATLAB code example as well. I need to. What do we have here? No, okay. First, I think you need to understand that for this you need MATLAB. Do you have MATLAB or not? If you don't have MATLAB, that's not a problem, because at MATLAB homepage, MathWorks, it is possible to use for free for students, and not only for students, MATLAB online version. It is very powerful. It is the last version. You just need to choose how do you want for free to use it. There are two possibilities. To get one trial for a month, but for a month it means that month, not a calendar, but month of work. So really very huge time period, because you need to program for a month real time, not calendar. So it's quite enough. Or you could choose 20 hours per month. So it's enough as well. So you could go online and to use it. Of course, you could use a free version of MATLAB. It's called Scilab. It's open source, like an open office, alternative to Microsoft Office. So it's called Scilab. It is free. Of course, it has a little bit less options, but for our task, this is quite enough. The only one you need to make some changes in syntaxes. Why? Because, for example, in MATLAB, this is common. In Scilab, you need to write this percentage sign if you want to say it is a constant. For example, P constant mathematically. MATLAB understands P automatically. It's a constant, but Scilab understands all constants only with this sign. What's more, if we're talking about the complex real and imagined mathematics, complex mathematics. Yeah. In MATLAB, very often we don't use I letter. We could use J letter. It is okay. For Scilab, you need to use only this with percentage sign. And for example, here we have a special function for calculation. It calls Zeidel, because this calculation uses Zeidel method. For MATLAB, it's enough that this file with function description is in the same folder as a program, because MATLAB automatically, okay, it sees the unknown name, so it understands this is a function and tries to find this function in the folder where you run your script from there. For Scilab, there is a different way how to call a function. So if you choose to Scilab, you just need to use like Google some help to understand how to adopt this code to Scilab. But this difference is very few. But as I said, you could use for free MATLAB online, no problem. Or you could come to this room and to use RTU MATLAB as a student, just to log in student, and to use MATLAB here, whatever you wish. Okay, so let's continue with this code which is written for you. What do we got here? Of course, I'll change these comments because it's in Latvian to English, but it's very simple. L, this is line lengths, this is resistance, reactance, and so on for every element. This is for is made for any example, so it means that you need to adopt this for your network. So, because for example, this is, you see, here we go, for example, 4 lines, you have 3 lines, and so on. So this is just input parameters about what do you have, how many transformers do you have, what are the reactants for every transformer, how many lines do you have, what is the impedance of the line. So you need to multiple the impedance for 1 kilometer to length of the line. So very simple. This calculation, you need to just write your values, input values. What is more interesting and more complicated is next. Okay, here it calculates the full impedance for positive sequence, for 0 sequence. Yes, so use all these values for previous calculation. What is very important to know for you? Here we have 3 matrices. First, second, and third is with resistances, with electromotive forces, and this topology with nodes and branches. Where to put? And if you understand that the number of branch should be the same in every matrix and in this when you calculate the values. Okay, what is important for calculation and for your information? First of all, when we draw this, some laws about how we draw. So, what is the difference in schemes? Positive, negative, and 0. Basic difference. You see that in a negative sequence, we don't have electromotive force. Electromotive force appears only in positive sequence. This is the first gap. We don't have these ETS values. Another one, we have different values for generator impedance in negative sequence. Here in your example, there are systems, not generators. For systems, we very often ignore system impedance because we call it system with infinitive power. If we have infinitive power, we don't have impedance. But if you have generator, you have an impedance of the generator. And negative sequence generator impedance is different from the positive sequence. So in negative sequence, we don't have electromotive force of the generator, but we have impedance of the generator. And in your code, yes, in your code, let's come back, yes, there is a remark for you to remember this. Okay, let's look through the generator. Yeah, here you go. This is the XJ, so generator reactance. It is here, yes? And how to calculate formula is here as well. But here you got the generator, yes? Generator 1, digit 2, digit 2, digit 2. This means that these two rows is for generator negative sequence calculation. So reactance calculation. And this is good for you to remember. So standard digits to index the sequence. Number 1 for positive, number 2 for negative, and 0 for 0 sequence. That's why we have this index 2, 2, 2. And this coefficient to multiple to the positive sequence generator value to get this negative sequence generator reactance. Okay. Go next. What other differences do we have? So here only 2 points. Yes, no electromotive force and different generator reactance. What is about the 0 sequence? In 0 sequence, we don't have electromotive force. We don't have generator impedances or reactances. We don't have. The only what is the difference is the line impedance. The line impedance is different. Here, line impedances are the same, transformer impedances are the same, but in 0 sequence, line impedance is this is average value, about 3 times greater than positive sequence impedance. Of course, it depends on physics about this line construction, phase construction, the distance between the phases and the phase and ground, real distance. But for our purpose, we could take this every value of 3 and it is enough. For example, here this is, you see the digit 0, it means that index 0, this all is for 0 sequence, and for this 0 sequence, where we go this number, the digit 3 coefficient, okay, just want to find out where it is. This is for generator, this is for electromotive force. And of course, okay, some different values. For example, for voltage, when we have 110, we understand that this is nominal voltage for your network. This is standard values because all values are standard. We have voltage of 10, 20, 110, 220, 330, 500, and so on. This is the standard voltage values. Here in your example, you see this is 110. It we understand that this is 110 volts. Kilovolts, to be true. Okay, where do we go? Where do we have this coefficient for 0 sequence? Okay, it is A2. It is here. This is A2. Here you go, A2. Now, in this example, this is 3.2, but as I say, you could use an average value of 3. Yeah, this is a coefficient when we multiple. Positive sequence, yes. And R1 and X1. So when we multiple positive sequence by 3 to get the 0 sequence. And this is all about these special issues. What do you need to remember. So what is the difference between sequences? And what do you need to get as a result? So you will get the two vectors, so two columns. One column is for current and one column for voltage. And here in this code, it is here. So as a result, you will get the U value, voltages, and IZ currents for every branch. When you got all of this, the next step is to make vectors of every phase. What will see the protection device, and for every sequence. But this is, how to say, the next step, and this step could be done only when you are sure that your currents and voltages are correct. That's why I suggest you to first to finish this, and only next we'll discuss how to use these voltages and currents to draw vectors for every phase of your system. So to know what is the current vector, what is the voltage vector for every phase. Okay, for today from theory, this is all what I wanted to tell you. Because I want, how to say, I don't want to explain too much. Maybe you have questions. So this video will be available, and this code will be available for you. I just need to translate these comments to English, and for this, yes, I just cut from this book for this digest, yes, just copy these images with comments, what and how. So these documents will be available for you.
This also, this PDF also.
Yes, because this is an example. This is a basic for you. Using this example, you need to do for another scheme your calculation. Yes. Not easy, but not impossible.
When we want to submit that task.
Okay, this I understand. This is very simple. When you submit this task, you will get a mark, a grade.
Oh.
If you don't submit, you don't have a grade for this subject.
Total 3 practical questions.
Sorry?
Total 3 practical questions.
3 tasks.
Yes.
Yes, you have only 3 tasks. So, but you need to do all 3 tasks to have a grade. So it's not enough to do only 2 and you have any grade. No, you need to do all 3, and the mark depends on how good all 3 are. So it's not enough to do 1 or 2, all 3. First is very simple. Okay. Because you just need to choose time delays for protection device. Second is a little bit complicated, but you have all steps how to calculate and all formulas presented. The second is you just need to calculate set point for 1 over current protection, and this all. And this third one is, yes, the most complicated. Then you need first to make an equivalent scheme. You need to put all your input data to the MATLAB. You need to get the correct calculation for every current and every node and every voltage, and then to design, to draw a voltage diagram for the protection device. Yes, this is more complicated.
That will pay the documents.
in Ortus. For now you don't get access to these documents, yes, but I need to how to say to prepare these documents for you and to ask to place these documents in Ortus.